So where does this idea of the block come from? This idea that there can't be a present moment that Einstein was so strongly attached to. We need to backtrack a little bit and fill in some physics here. So in Newtonian physics, there is, as is well known, a nice single surface that can separate past from the past from the future, right? There's a unique now, and all observers can agree, and you can use this to synchronize distant clocks and so on. There are worldwide instants in this universe. In special relativity, we lose these worldwide instants. Special relativity is built from two basic principles: that any inertial frame will do for physics just as well as any other, depending on, doesn't matter your state of motion, and that the velocity of light is constant in all of these frames of reference. Now that looks like quite a tricky thing to secure, and Einstein's great genius was to figure out how to make these two things consistent. To do this, this is the fastest introduction to special relativity ever. We use these space-time diagrams. So we have space going across the x-axis, and then t is going up the slide on that t-axis. The speed of light, well, velocity is represented by this red line here. Velocity, remember, is just a rate of change in position with respect to time. So it's if light is given the maximal velocity, then that just means that in 1 unit of space, you're traversing 1 unit of time, we can say. To say that it's constant means that it always needs to traverse 1 unit of space in 1 unit of time. But that seems to conflict with certain intuitive facts about the world. So let's see what Einstein's solution to this problem is. So we'll imagine a pair of observers. We've got Angela and Boris. We're in Angela's reference frame, so she just simply moves up her world line here. Boris is going to be running rapidly away from Angela, so he makes his world line is tilted relative to Angela's. The light ray is there, as you can see it, 1 unit of space and 1 unit of time. Now, although in Angela's frame, light is moving 1 unit of space and 1 unit of time, in Boris's, because he's kind of chasing after that beam of light, he's moving more units of space in the same number of units of time. So that would mean that the light ray is traveling at a velocity of less than c, according to Boris. How does Einstein deal with this? Well, he says that in order to preserve this constancy of the speed of light, we must tilt also this space axis as well. This space axis is the set of events that Boris considers to be now, to be present. The blue space axis is the set of events that Angela considers to be now. And you can see if we tilt Boris's up a little bit, then we preserve once again the fact that light is moving 1 unit of space in 1 unit of time. So what this means is that there'll be certain events that Boris considers to be simultaneous, that for Angela, they will be successive. P comes before Q for Angela. P and Q are simultaneous for Boris. What this means is that there can be certain events, for example, Brexit being done, which Boris would say is now, but would be in the future for relative to Angela. So these two observers kind of intersect. If they're running at a motion relative to one another, then Boris will have a bunch of events that are not that are simultaneous for him, but that are future for Angela. And then the idea is we can find any number of observers to build up the whole of space-time in this way, so we end up with a block in which things have already happened for some observer. What this ends up revealing is that in this 4-dimensional universe, well, we've got entire world lines of humans and objects and all sorts of things given from birth to death once and for all. The passage of time is like the unwinding of a rope, producing nothing new, but unfolding what was there at first. And it's precisely this business of producing nothing new that bothers people like Lee Smolin, who thinks that surprise needs to be a feature inherent in the structure of a world. So he writes in this book, The Singular Universe, that the block picture is horrifying to anyone whose worldview includes a place for free will or human agency. Why? Well, because he thinks things like the climate catastrophe, whether we survive the climate catastrophe or not, have already happened in the block. So there's nothing that that we can do about it from our present position. Now, his he's pretty naive philosophically in this sense, because there's no reason to think that the block is inconsistent with there being consequences for embedded observers in the block. There's no reason to think that the reason the climate catastrophe was resolved or not wasn't due to the actions within the block of agents who perform certain events which are causally linked within the block. But we'll leave that aside for now. I'm just trying to present his view for now. So Smolin isn't alone in this. There's a number of people that I'll call blockbusters who are trying to present new views of physics in which time is fundamental, and they often rely on what seems to be the obvious experience we have of a changing dynamical world. One of these is Faye Dowker, who's another quantum gravity researcher. So she writes that our inability to reach consensus on the passage of time could be a consequence of our not yet having made the necessary scientific progress. We do not have a successful theory of space-time that coherently incorporates the quantum nature of the physical world, so we do not yet know the nature of the deep structure of space-time. And some of the observational facts on which the new theory will be built may therefore now be only roughly communicable, and our sense experience of the passage of time might be an example of such a fact. Well, as we've seen from that very brief study of our sense experience of the passage of time, things are not so easy, and it's incredibly complex to even make sense of what we could mean by our sense experience of the passage of time, let alone using that as a basis for a quantum theory of gravity, as Faye Dowker does. I mean, Faye Dowker has her own approach to trying to incorporate the passage of time into physics based on this approach called causal set theory, which involves the birth of new bits of space, what she calls the birth of space atoms, which she thinks sort of introduces a notion of objective becoming or passage in the universe. I'm not convinced by it personally. We can discuss that. Another approach is this one of George Ellis. So George Ellis bases his on quantum theory and the quantum measurement process. And he's concerned with the fact that there seems to be a transition from potentiality to actuality in quantum theory. Before we make a measurement, there's a potential set of events that could happen. And then we make a measurement and there's one single actual outcome, a happening in the world. So he thinks that should be enough to ground a notion of flow and real transition in the universe. And it's another argument from experience, essentially. So he writes that the present is different from both the past and the future, which in turn are completely different from each other. The past being fixed, the future being changeable, the present is the instant of transition between these two states. It's this fundamental feature of time that is not captured by today's theoretical physics, even though it is a most obvious and crucial feature of everyday life. So again, he's relying on the fact that there seems to be this obvious experience that we have of change and passage in the universe. Again, not particularly convinced, and it's mostly sort of statements rather than arguments. Another example is the approach by Christopher Fuchs, who bases his ideas on the physics of John Wheeler. So in this approach, which he calls cubism, quantum Bayesianism, you view quantum mechanics as about agents and the sort of the actions of agents on a quantum world. So rather than thinking of observers who passively watch the universe and watch the outcomes of experiments and so on, a participator is something that gets to decide what experiment to perform in a quantum mechanical experiment. So for example, you might decide to perform in an experiment to measure one axis of spin rather than another axis, or to measure position rather than momentum in a double slit experiment. And in deciding as an act of free will which one of these to perform, you get to create the future state of a universe, which is not decided in advance, because there are certain theorems in quantum mechanics, such as the Koch and Specker theorem and Bell theorem, that say that there are no hidden variables and these things aren't decided in advance. So you sort of play a role in creating how the universe evolves into the future. It's almost an existentialist approach. As he writes, our actions matter indelibly for the rest of the universe, for quantum mechanics signals the world's plasticity. With every quantum measurement set by an experimenter's free will, the world is shaped just a little as it participates in a kind of moment of birth. I'm a little bit more hopeful about this particular approach to injecting time into the world because it's based on John Wheeler, and I'm writing a biography of John Wheeler. And then finally we get to Lee Smolin's approach. Smolin's argument, as I said, seems to be based on this hope more than anything that we ought to be able to intervene in the world in order to solve various crises and so on. It's like a modern version of Aristotle's problem of future contingents, in which Aristotle spoke of whether there would be a sea battle or not tomorrow. So Smolin writes that the aspect of time I assume is irreducible is its activity as the generator of novel events from present events. He gets his the basis of his argument for putting time back into physics from a very unlikely source, which is from a theory of the arch enemy of time. So Julian Barber here. So he wrote a book called The End of Time, in which he thinks that the universe is genuinely atemporal. There are only spatial configurations with no temporal link through them whatsoever. So there's a configuration space, three-dimensional configurations, and there's no temporal connection between them whatsoever. But what he uses of Julian Barber's is a new formulation of general relativity that Julian Barber came up with, known as shape dynamics. And in shape dynamics, there's reintroduced a well-defined notion of instantaneous spatial configurations. So we have something that can perform like these worldwide instants again that were eradicated in special relativity and in general relativity. So Smolin writes of this theory that in general relativity, size is universal and time is relative, whereas in shape dynamics, time is universal and size is relative. Remarkably, though, these two theories are equivalent to each other because you can, by a clever mathematical trick, trade the relativity of size of time for the relativity of size. And the physical content of the two descriptions will be the same, and any question about an observable quantity will have the same answer. And it's obviously too tricky to go and explain what's going on in this theory right now, but what I will say is that there is in this approach of Julian Barber's, which has a well-defined notion of present, but you're allowed to rescale things, resize things at distant events. So there's a relativity of size, but not of time. But so one thing that has to stay the same, which is not allowed to vary, is the overall volume of the universe at each of these instants. So that makes the overall size of the universe and its expansion meaningful. And then you can use this as a universal physical clock. So it looks like time has been rediscovered in this approach. And this is exciting for Lee Smolin for these reasons. So he says, shape dynamics just by its existence has two important implications for the present argument for the reality of time. First, the impressive empirical success of general relativity can't be taken as evidence for claims that the universe is fundamentally timeless, or even that there is no preferred simultaneity of distant events. These common claims are nullified by the fact that there's an alternative formulation of general relativity that does feature a preferred simultaneity. Second, the preferred slices of shape dynamics give us a candidate for a global notion of time needed to provide an objective distinction between past, present, and future consistent with current scientific knowledge. Okay, that was a very quick description, but all I can manage in this time. So where do things stand? Well, philosophers and physicists interested in foundational questions are in a curious spot, because whereas it used to be easy to simply refer to relativity to point out that the old-fashioned idea that time flows with one moment now turning into another moment must be false, we now face a dilemma if this shape dynamics business is true, in that the raw structure of general relativity can be given different meanings. One would be three-dimensional and consisting of instants. The other would be a block, a four-dimensional block. So the task then facing us is to make sense of these dualities, which is a philosophy of science issue, because it looks like our best physical theory of space and time seemingly can't determine the ontology of time. So we don't know where time is or where flow is, because its empirical success can't be used anymore to tell philosophers what to think. At the same time that we've got this situation in physics, philosophers seem to have swallowed this illusion story and believe that flow is not a part of the world, following mostly older physics. So we have this curious switch where a new wave of physicists are putting time center stage and using our experience as part of that, without realizing that it really isn't simple at all, the notion of our experience of time. And then we've got a new wave of philosophers throwing time out using the claims of physicists like Ravelli and so on in classical and quantum gravity, without realizing that the physics isn't that simple either. So we'll leave things hanging there with this interesting new set of problems. I think it will take the efforts of physicists, philosophers, and neuroscientists to disentangle what's actually going on here, taking full account of the complexities of each. This is an example of an inextricably interdisciplinary problem